Hopefully that'll work. We'll see. Um, we have already discussed this to a certain degree, but just to kind of clarify a little bit, gravity is that force between two objects. So, believe it or not, Sean and Sophie, like, they're attracted to one another. Okay? It's odd, but it's true. And because they are two bodies of mass, you look upset about that. It's okay. It's okay. Everybody is attracted to everyone in this sense. Okay? If you have mass, and you're made up of matter, then you are going to be attracted to another object that has mass and is made up of matter. How come you guys don't feel the attraction? Why is Sean just out resting his head on your shoulder?
Oh, because Sean's not a magnet.
Okay? Well, there's probably lots of reasons for that, but the main reason is because you guys don't have enough attractive force because you're not massive enough. However, if you guys were planets, or at least the size of planets, then yes, you would be attracted to the point that one planet would start to orbit the other. We see this when we talk about celestial bodies, when we talk about planets and stars, that's when we start to see that effect. That's when gravity really becomes a key component in how these systems organize themselves. An example for us, we are large enough as Earth to have a natural satellite. We've captured this big chunk of rock, and now it just floats around us. What do we call this rock?
Massive thing of cheese.
Yes. Some people say it's made of cheese. The moon, there it is. Yes, that's called a natural satellite because, like an artificial satellite, it circles the Earth. Okay, it is captured by us. It cannot escape our gravity. In fact, I believe, actually, I guess it is slowly escaping. It's getting further away each year. So one day, the moon will probably be gone. You'll be long gone too, so don't worry about it. It's not going to be a big deal. But not only is the moon attracted by our gravity and captured by our gravity, but the moon influences us with its own gravity. Now, in what way does the moon influence us through its gravity? The tide, very good. So literally, at a certain point in time, when the Earth is rotating around and the moon is above the Pacific or Atlantic Ocean, the gravity of the moon actually pulls the water of that Atlantic or Pacific Ocean up to the point that it takes it away from the shore. It's almost like, I don't have a sheet or anything, but here, we'll use this guy. If I take this little rag here and I pull at its center, what happens to the sides? They come out. That's the same thing that's happening with the water. The moon pulls at the center of the water, and the tides go away from the shoreline. And then when the Earth rotates back around, and the moon is no longer in front of it, they relax, and the tides go back in. This would be low tide. This would be high tide. Okay, make sense? All right. So of course, gravity does have an influence. It's not only that, it's acting on us all the time. Okay? Anybody here ever been to like Six Flags or Disney World or something like that? You walk around all day long. What do you want to do when you get back home? Sleep. You want to just go to bed, right? That feeling, that relaxing feeling that you get when you pour yourself into bed or you pour yourself into a comfy chair, that's your muscles finally relaxing from the force of gravity that has been working on you all day. Now, there's other things that you're probably tired from, like walking through an amusement park for hours on end. But the reason that that's tiring is mainly because of gravity. So, falling objects in particular have two forces that act on them. One is, of course, gravity. The other is air resistance. So gravity is what causes an object to accelerate downward. You experience that anytime you drop something or you fall. But air resistance actually pushes the object back up. We talked about that a little bit earlier when we talked about fluid friction and how, or you guys remember that little demo that we showed where the paper clip with the aluminum foil that was spread out? It sunk slower or faster? Slower, right? The aluminum foil acted to increase the surface area of the paperclip, thus causing it to go slower. Guys, this is the same way that a parachute works. Okay? Anybody here have, like, on their bucket list to jump out of an airplane?
Yeah.
Okay, and hopefully, skydive. I hope you're not just jumping out of an airplane. That's not the right. Okay? That's on my list. It's not on my wife's. She has no desire whatsoever to do that with me. And I have no desire to do it alone. Okay? The day that I do this, and I am going to do it one day, I'm going to be strapped to some guy or girl, I don't care who it is, who knows when to pull that cord at the correct time. I don't want that to be left to me. Okay? Because, sometimes you just make mistakes in life. And I might make a mistake in that moment, and that would result in kind of a pretty difficult situation, right? Kind of messy.
I've also seen people, pass out.
Yeah, I mean, there's so much that could happen. Like, I could pass out, and then, that's the end of me. I always thought it was funny. I mean, this has been said before, so I can't take credit for this observation. But I think it's really funny that skydivers wear helmets.
They do?
Yeah, they do. I don't really think that's going to do much for you in the event that the parachute doesn't work. I think one comedian said that at that point, you're not wearing the helmet is wearing you. There you go. All right. So, there are some animals that take advantage of air resistance. What you got down here is a sugar glider. You guys ever seen these before?
No.
Okay. It's basically just a squirrel with wings. Now, squirrels don't have the ability to flap the wings and actually create enough lift to propel themselves into the air and fly. But what they can do is they can glide. So they use the same principle that somebody in a flight suit would use, and they increase their surface area, increasing the amount of air resistance that comes into contact with them, and that allows them to stay airborne for a longer period of time. Some people have these as pets, and you will see them, they'll hold them up, and they'll hold their other hand up, and they will glide down to their other hand. So they're kind of cool. I don't think I'd own one, because, I have this thing against owning rodents, but whatever. We good here?
Yeah.
All right. We kind of talked about this before, but with increased speed comes increased air resistance. So the faster you go, the more air pushes back on you. It's the same thing I think I said last time. As Michael Phelps swims through the water, the faster he swims, the more the water pushes back on him. Eventually, that upward force equals the downward force of the pull of gravity, and the acceleration stabilizes. Does that mean that you stop falling? No, nobody ever stops falling. It just means that you stop accelerating. So at a certain point, the velocity doesn't change anymore. You reach a certain velocity, a certain speed, and you stay at that speed. Okay? This is called terminal velocity. It's the highest velocity achievable. That will work?
No.
Okay. So again, terminal velocity is the constant velocity of a falling object when the force of the air resistance equals the force of gravity. You're falling so fast and for so long that you max out your speed. Okay? Now, can you achieve that? Like if I drop something from here, is it going to achieve terminal velocity? No. You have to be in the air for many seconds in order for you to achieve that. If you'd have to probably fall from several stories up before you reach terminal velocity. But that would be the maximum amount that the wind resistance would be pushing up on you, stopping the acceleration and thus creating a constant speed. All right, we good? We are going to, by the way, guys, I know I feel like I'm going through it. I apologize. If you need me to slow down, that's fine. But we are going to do a lab today, so I'm not gonna lecture at you the whole time. Yay. You guys seem tired today.
Yeah.
only Wednesday.
Not bad.
Just check your watch to see what day it was.
Yeah.
Then, oh, yeah.
All right. Good? Any questions? Terminal velocity, fairly straightforward. Now, let's talk about falling things, though, for a second. Okay, I'm going to try really hard not to break this, because, you know, I like having two of these. But I have this down because I don't want to break the tile. If I break the recycling bin, okay, you know, that's probably not good, but at least it's not that bad. I need to buy one of those things. Like, apparently there's one thing that, like, will follow you around. Yeah, like a tripod that does that. So, I have two objects here. One is a stone, okay, has relatively a large amount of surface area. It's kind of flat. The other one is a pair of scissors. Now, which one, if you could for me, which one has more mass? The rock, okay? Would you agree? It's good to have multiple sides. Okay, so then which one do you think is going to accelerate faster towards the ground? Raise your hand if you think scissors. Okay, and I'm only using scissors because I don't really have anything else. Okay, raise your hand if you think rock with its more mass. Well, this leads to kind of a central question. Do things that have more mass accelerate faster?
No.
Or is everything accelerating at the same time?
Same time.
What does the acceleration do to gravity again?
9.8 meters.
9.8 meters per second. Is that the same for this rock as it is this pair of scissors?
Yes.
Now, what about, what else influences, though, the speed of falling?
Air resistance.
Air resistance. So is that going to have an impact? Okay, so raise your hand if you think the scissors are going to hit the ground or hit the inside of this bin first. All right, just a couple, 3. Raise your hand if you think the rock. Okay, it's going to be kind of hard for you to tell the impact because obviously it's going into a container, but I want you to listen for it. Okay, so I'm going to try to lift these up over the bin here, and I'm going to try to drop them at the same time at the same height. Ready? 1, 2, 3. What do you think? Raise your hand if you think rock hit. Scissors. Again, you got to hear it. Raise your hand if you think both hit at the same time. All right, a good experiment needs multiple trials. Okay, we're gonna try again. Falling in 3, 2, 1. Okay. When you listened to it, did you hear it dun or did you hear it boom? Raise your hand if you thought that you heard the same sound when they both hit at the same time. Raise your hand if you think that they did hit at different times. Okay. So here's the thing. In a small enough setting like this, where we're not reaching terminal velocity and we don't have a ton of air resistance because we're inside, so there's not a lot of movement of air, more than likely these hit at the exact same time. Okay? Which seems counterintuitive because you think that this is going to hit much faster. Now, let's say I increase the surface area even more to something like a piece of paper. Now, which one's going to hit first?
Rock.
We all sure? You guys would be really shocked. But I think you guys are right. Obviously, it took a lot longer for the paper to fall down. Now, we know that to be the case. Why? What's causing the paper to go so much slower? The air resistance. So, what if we could take air resistance out of the equation? Okay, let's find out.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
What do you think?
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
We dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
This is what happens when you take the air out too quick.
They came down exactly the same.
Exactly the same.
Feathers don't move, nothing. Look at that. That's just brilliant.
Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this: the reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the earth. So he concluded they weren't.
All right. So there he was talking with Einstein about points of reference, which we talked about earlier. But really interesting stuff. I've watched that clip several times over the past several years, and it still always kind of fascinates me that the feather never moves. The ruffles of the feather stay exactly intact, stay exactly the way that they were the entire time it falls. So that leads us, though, to projectile motion. We don't have too much left, guys. Just a couple more slides. And then we'll take our break. And then we'll do give you guys a second to get this down. So very rarely, at least when it comes to our own personal use in this case, we're never going to just drop something. Very rarely do we do that. We oftentimes propel something, which means that we give it a initial velocity first, and then gravity kind of takes over from there. Because it's impossible for us to constantly force an object, especially a projectile. But when I think about this, I think about sports. Of course, I think about bullets from a gun. I think about missiles. I think about our trajectory with certain rockets when we launch them into space. We want them to hit something, right? We want them to go to something. If we launch a rocket from here and we want it to go to the International Space Station, it's not going to be very good if it lands on the other side of the Earth. Okay, that's not what we're after. We need to map out its course and figure out exactly where it's going to end up. Okay, that's where this idea of projectile motion kind of comes into play. It's the motion of a falling object, a projectile, after it's given that initial forward velocity. Right? So when I think of this, the first thing that pops into my head, I coached track for 1 year. I threw shot and disc. I didn't mean to actually wear the shirt, but it just works out. I threw shot and disc when I was coaching, or excuse me, I threw it when I was in high school, but I also taught it when I was coaching. This idea of projectile motion comes into play quite a bit. What are you trying to do when you throw a shot put? Throw it far, right? The farthest throw is the winning throw. And it's not the farthest as to where it rolls or something like that. It's the farthest to where it hits. So it needs to stay in the air as long as possible, right? Okay? So if you want to achieve maximum distance, what do you have to do?
Give maximum strength.
Yeah, you give maximum strength, obviously. Okay? How would you throw it though? You have to push it off of you. You can't throw it like a baseball, and that's actually more of a safety concern. If you try to throw it like a baseball, what do you think you're going to do to your elbow?
Break it.
You're probably going to break it. Yeah. If you really did, we're talking about this is it's a 12-pound ball in high school. In college, it's a 16-pound ball. This is not light by any means. A heavy bowling ball is about 16 pounds. So it's imagine throwing a bowling ball. You can't just throw it like a baseball. Okay. So what's the best way to do it?
Use your hips.
Yeah, absolutely. You're right. Use your hips. But I'm thinking more of the projectile. Do I want to throw it up high? Why? What would happen? It would go up really high, but would it go far? No, it would just come back down and have a really shallow curve. Really high arch, really shallow curve. What if I threw it straight? What if I just threw it like this? So it would go with pretty good force, but would it stay in the air for very long? No. And as soon as it hits, remember, it would probably roll really far, but it wouldn't stay in the air for very long. And we don't want it to roll far. We want it to land far. Okay? So what do you think the best angle of projection would be for a shot put? 15? Yeah, 15 would be like if this is parallel, 15 would be like right here. So like if this is straight, what do you think? I'm sorry? Underhand? Well, you have to, like you said, you have to throw it like this.
I know it's like
So like down here?
not down here, but like
So how about this? I'm going to start here at straight at 180 degrees. You guys tell me when to stop, when you think it's the best.
Stop.
Probably right here? So about 45 degrees, which is pretty much right where you're at, is the best angle to throw the shot put, have it stay in the air the longest, and land the farthest away. Okay? The other thing that you want to do is you want to keep it on your hand for as long as possible. The reason for that is because it continues to accelerate for as long as you have it until you release it. After you release it, what starts to work on it? Gravity, and it starts to slow it down. It resists that force. There's also wind resistance that's causing friction that's slowing it down too. It's the same thing with a gun. Does a long-barreled rifle shoot farther than a short barrel? Yes. Yeah, for those of you who maybe know about guns or not, a long gun is always going to shoot longer than a short gun. Okay? A pistol can be accurate up to like from here to that column. Okay? If you're really good, you might be able to shoot accurately from here to the end of that wall there. Okay? After that, it's not accurate at all. But if you have a rifle, You could be accurate for 100 yards, 200 yards, 300 yards. So we're talking about 3 football fields. Okay? There's a big difference. And one of the reasons for that is because of the longer barrel. That's just one reason, but it's a big one. So, because of the combination of the initial forward velocity and the downward vertical force, every projectile will always follow a curve. Think about throwing that shot put. It starts up, goes high, it reaches its peak, and then it falls back down. You want that curve to be as broad as possible so the distance is as broad as possible. But no matter what you throw, it's always going to have that projectile curve. All right, we won't worry about that. Let's talk a little bit about Newton. We have probably 2 slides on Newton, and then we're going to take our break. Okay. I don't often give time and give slides to honor a scientist. There's a few that I do. Newton is one of them because I think he deserves it. He's considered the father of modern physics. Listen, if you're the father of a science, then you're doing okay. You did a nice job in your field. You got a lot of recognition. Congratulations. I want you to understand, guys, one of the things, I said this in the last class, and this has nothing to do with today's lecture, but I want you guys to get that we're not done with science. I would argue that there's still stuff to be learned probably in every subject that you guys go to today and tomorrow, but science is probably even more so that. Some people will look at this and go, well, he discovered this in 1687, so obviously physics hasn't changed much for the last 100 years, but it has. Science has changed a lot in the last few hundred years. We've invented new sciences. You guys know that? That 70 years ago, we invented genetics. Okay, we didn't have it before that. Right now, we are just starting a new phase of computer engineering. It's called quantum computing. We know very little about it. It's a brand new field of science. So I don't want you guys to think when we learn about these really old guys that these guys taught us everything we know and we haven't achieved more since then. Okay, there are 3 companies right now. Well, there's more than 3, but Panasonic, LG Chemical. We talked about John B. Goodenough and how his group is doing it too. Samsung is even doing it. They're all working to make a new battery. They're using new cell chemistries to make a better, longer-lasting, more efficient battery. Science never stops. So if you guys want to get into a field that is constantly innovating and constantly changing and getting better all the time, I really think science is a good choice for you guys. I think healthcare is kind of along that line too. I really hope that when I'm old, they don't treat most of the illnesses that we have the same way that we do now. I hope that we innovate, that we change, and that we become better at it. So, in a lot of ways, we didn't. There's some things that we need to work on still, but a lot of ways we do. So don't look at this and see 1687 and just think, okay, well, this science is just old. It is old, but it's still changing. It's still revolutionizing the way that we do things. So he penned a book back then in 1687 called the Principia Mathematica, which just means his math principles. That's all he's going for there. And in that, he described his 3 laws of motion, which we're going to highlight today, or we're going to start to highlight. The first one being the law of inertia. Go ahead and get this down. Also like to show you that picture of him. He was a handsome fella. Him and his wig. His French wig. Or he sounds English.
Didn't he go crazy and start working at a bank?
I don't know what happened to him in his later years.
I think he went crazy.
I mean,
Worked at a bank.
usually, guys, if you're kind of a genius, you sort of skate between the line of crazy and insane. Most people that are incredibly smart are much more likely to get dementia, much more likely to have split personality disorder, much more likely to have most of the mental issues that we see today. And I don't know what the correlation is there, but there is definitely a correlation between extreme intelligence and cognitive function. It's almost like you work your brain too much. It's good every once in a while to kind of just veg out and play like 1 or 2 video games. Not the entire night. Just like 1 or 2. Or maybe sleep. That might be good too. So this was actually, Newton gets all the credit, but this was actually given to him by his mentor, Galileo, that same dude who figured out most of the planets and the order of the solar system and all that good stuff. But he had this idea that an object at rest tends to stay at rest, an object in motion tends to stay in motion in the event no outside force acts on it. Guys, the best example I have for this is a sad one. If you have ever seen a car accident of someone who is not buckled into their seatbelt, what happens to them during the accident? They are projected through, as a projectile motion, projected through the windshield, and they land somewhere outside of the car. Okay? The reason for that is because of Newton's first law of motion. That object, that person, was in motion in the car. If they were going 60 miles an hour, that person, you guys don't realize, you're going 60 miles an hour. You are traveling at that speed. Even if the car stops, you will want to maintain that speed. Which is why if the car suddenly stops, you will continue going 60 miles an hour unless you have some sort of restraint that slows your acceleration down to the point that it's at zero. It's that sudden change in direction that unfortunately is what kills people. Okay, I'm going to show you guys an image of this here in a second. But we summarize this first law of motion by calling it just the law of inertia. Okay, inertia means just that. That something in motion wants to stay in motion. It has inertia with it. All right, anybody need more time here? So I kind of just mentioned this, but I want you guys to get it down. So again, here we have a definition of inertia. It says the tendency of an object to resist a change in its motion. Listen, guys, if I ran directly at this wall right over here is not made of concrete. It's just a regular 2x4 and drywall wall. Okay? If I ran directly at that wall at top speed, what would happen? I'd probably put a hole in it. I'd probably break through that wall. Now, would that feel good? No. Should we test it?
Yes.
Okay. What if I went at a just sort of a slow speed and I hit this wall? And nothing happens, right? It stops me. It's able to take my inertia, even though I want to continue forward because I've given myself some acceleration, it's able to take that and to stop it. It stops my acceleration down to zero. It stops my velocity down to zero. But if I ran at it at full speed, okay, as fast as I could go, I weigh a pretty good amount, I would deliver quite a bit of inertia. I would probably break through that wall, right? Now, like I said, it would hurt. It would not be fun for me, and I think I'd have a lot of explaining to do to people in the main office. But I could probably break through it. That's that idea that an object in motion, normally that wall would stop somebody from just walking into it, right? It wouldn't just fall apart from that. But an object in motion, if you create enough motion, you create enough force, that wall's not going to be able to withstand it. Okay, it makes it more difficult for me for it to stop me. If somebody's running really fast and you're not prepared for it, are you going to be able? If they hit you, what's going to happen to you? You're going to take some of that momentum and it's going to transfer to you, and you're going to fly off to the other side. Okay, you're probably not going to stop the individual, especially if you're not prepared for it. Again, this goes into, I told you, there's a lot of this sort of science with sports. It's a lot with football. Anybody here ever ran the football? Like been I don't know, a halfback or something?
I'm a wide receiver.
Yeah. You've been a wide receiver. So when you get the ball, what do? You tuck the ball and then what do? You run as fast as you can. If somebody's coming at you, you try to evade them, correct? You want to get away from them. Okay? But if you have a line of people and there's no way for you to get out of the way, what do?
Sometimes you slide.
Sometimes you might slide, all right? What's the other option?
He must be using what I did.
Okay. All right, he didn't want to get hit. The other option is you try to run as hard as you can through them. They always say for most of the running backs that if you want to not get hurt while you're getting tackled, because a running back is a target, right? Everybody on the defense wants to tackle them. They say to run at them. They say to give them as much force as they give you. That's going to create. You're going to be harder to stop. Not only that, but it's also going to not hurt as bad because you're delivering as much force as you are taking. Okay, so again, there's a lot of science behind things. Behind most sports, but definitely behind football. In other words, an object at rest tends to stay at rest, an object in motion tends to stay in motion. So again, inertia, the reason we call it the first law of motion, sometimes the law of inertia, is because it kind of means the same thing. Now, I want to just show you guys what this looks like if you look at it in these stills. The reason I'm showing you stills rather than a video is because you can actually break it down. So this car, which is somewhat of an older car, but still, it's about to hit this wall. The wall is made of concrete and probably a lot of weight, and it's not going to it's going to withstand the crash, which means it's going to transfer all the energy of that crash back into the car. Now, when that happens, the first part of the car, look at the engine bay. It's completely crushed. Okay? There was enough force delivered in this crash to shred metal. What do you think that would do to a person? It would probably shred them, right? Okay, you wouldn't be able to withstand it. By the way, I should have said this. I should have prefaced this with this. If anybody's sensitive to car crashes for whatever reason, you're welcome to step outside for a moment if you'd like. Okay, but so far no one's taken me up on it. I just know that sometimes this can bring up bad thoughts. So. Obviously, you can see that the force of the impact was able to shred sheet metal, was able to shred an engine block probably made out of solid aluminum. Your body's not going to stand a chance if that force gets to it. Okay, and obviously the force is going to travel down the car until it reaches this individual. This person was going at the same rate of speed as the car. Now, there's two things that are being employed here to slow this person down. If you want to save a life, you need to slow down that individual from accelerating, experience the same deceleration as this car front, this engine bay. So what we do is we set off a airbag and we have a seatbelt. The seatbelt, I don't know if you guys know, but if you're ever in a crash, you have to replace the seatbelts. Even if like the seatbelts don't appear damaged. You guys know why? Nobody? So the seatbelts are designed to actually stretch. And they stretch so that they can actually slow you down as you go forward. After they stretch, they don't stretch back. They don't kind of just spring back. They have to be replaced after that. So the seatbelt stretches out. You guys can see it happening there. You guys have felt that seatbelt tighten. That will actually continue to stretch a little bit if you give it enough force. That slows you down slower than if you were just bouncing off the front of the steering wheel here. The other thing that stops you is your head's going forward because remember, you're going that speed, so your body wants to stay in motion. You get this big pillow of air, which we call an airbag. That hits your face and it engulfs your face and it slows down that impact. Again, instead of going right into the steering wheel, you now hit that and you slow down. You're still going fast. Are you still going to be sore? Yes. Are you still going from the seatbelt? Are you probably going to have a line all the way down your chest? Yes. But will you hopefully be alive? Yes. Okay? So, that's the goal. And then finally, you see the last little bit where the majority of the impact is taken by the airbag. It wasn't until, I want to say, 1998 that airbags became mandatory in all vehicles. This is a safety precaution. Obviously, they've saved lots of lives. To this day, it's not mandatory. I don't believe in the back seat, but a lot of cars have them. Behind head cushions and then side panels. There's some cars that have like 12 airbags now, all designed to slow down the momentum and the inertia of the people inside. All right, and here you can see the car actually bouncing back. That wall, it's giving a lot of energy to the wall. The wall finally gives the energy back, and you can see the individual flying back from that whiplash effect. And that takes us to Newton's second law, where we'll end today. I want you guys to get this down. We're going to do some problems with this next time, but you guys are going to actually practice it today. I gave you guys a triangle down at the bottom. Some people seem to like those. If you like those, that's fine. You obviously just have to cover up what you're looking for. So if you want to try to find force, it's mass times acceleration. You cover that up, and you see those two next to each other. You're always going to label force in newtons, which is, again, a kilogram meter per second squared. But when we talk about, and we'll pick up on this again next time, when we talk about Newton's second law, it's the relationship between force, acceleration, and mass. Okay? Force equals mass times acceleration, which means the more massive something is, and the faster it's moving, the more force it has. Again, that goes back to football. Okay? If you want to increase your force, and you want to make yourself harder to tackle, you have to get bigger, which is hard to do. But the second one's a little easier. You have to run as fast as you can. All right, you guys good? Get ready for your break. All right, go ahead and continue to finish this up. Let's do 2.5 minutes this side. Go ahead and use the restroom. When you guys get back, we'll do the other side.